I'm pretty sure we are recording right now. Yeah. Wait, it looks like it's cutting out a bit of this, the board right there at the corners. Okay, so welcome to the second tutorial video. So you were asking something about gravitational forces and stuff like that, like between the planets. All you have to remember is that the force, if you have two bodies, A and B of mass M and M, the force of A on B, or of B on A, since they're equal and opposite, is just going to be G, big G, the gravitational constant, times the mass of one, the mass of the other, divided by r squared, which is the distance between their centers.
But you know how on the exam they give formulas? The big G constant wasn't even on there. So that's why I was wondering if it was going to be on the exam.
I guess not. Maybe he just forgot to put it on there, but just remember it. Look, it's a constant, the mass of the two objects, and the radius squared.
And you can bring your own.
My teacher didn't say anything about that though.
Let's see.
In our lecture, we can bring our own cheat sheet.
Yeah,
And
I
we
heard
can write
about that.
whatever we want.
Just I don't know if my class is allowed. Like I made one, but I don't know if they could bring it.
Isn't it like
I think
everybody
you
together?
should.
Yeah, but like our teacher didn't specify it. So I don't know. Because there's this one and there's another constant, right? Like the K and there's like S or something. Like for different planets. You have to calculate it depending on which planet it is and the radius.
The K, what?
Like in the book.
I don't know about the K.
Yeah, there's K here, which is 2.97 times 10 to the negative 19. And then there's another one L, actually.
Oh, this is Kepler's third law. Okay.
And then there was another, like, I think it was L or something, and another one. But like, they weren't on the formula sheet, so I was like, I think we have to memorize that one.
Yeah, I would say don't worry about this. This is not going to be this shouldn't be on your test.
Okay.
They usually don't go into this much detail with like Kepler's third law.
Okay.
So this should be out of the thing.
This is something like calculate gravity, right? Like on Earth, like the 9.8.
Yeah.
But like, I was wondering if we're going to have to know something for other planets or something. Because you technically have to know the Earth's mass, you have to know the Earth's radius to calculate it. So I was like, would we have to memorize that kind of stuff?
Yeah, well, you can get that from this equation here. See, look, if you know G, the gravitational constant, then you can find out the force between any two objects, right? So as you can see from this equation, if you put your mass here and the mass of the Earth into here, and the distance between you and the center of the Earth, you'll get the force between you and the Earth.
We have to know the radius and the mass of Earth.
Yes.
By heart.
Yes. No, well, they'll be given.
If they begin to.
If you had to use this equation, they wouldn't expect you to know it. If somehow you forgot, you should be like, oh, sir, we need the mass and the radius to do this, or else we can't.
And they'll give it to you?
Yeah, they'll be given. But so look, basically the force that you're exerting on the Earth is the same as the force that the Earth is exerting on you, because by this equation, they're equal and opposite. Now, notice that I can rewrite this equation as the acceleration is equal to, and then if I divide this by if I know the acceleration on you, I divide it by your own mass. So if I divide both sides by m, I get that this essentially is just the acceleration, and that's going to be g m over r squared. See what I did? So essentially you can find out what the acceleration due to a planet of mass m is if you're a distance r squared away from it. And if you plug in the mass of the Earth, the radius of the surface, this will be equal to g.
Yeah, okay.
So that's how you would find the gravity on a certain planet. You'd use the gravitational constant, the mass of the planet, and the radius squared. Calculate the acceleration due to that thing. And if you multiply that by your own mass, you find out how much of a force that would give you. The same way, you can find out how much acceleration you're exerting on the Earth as well. It would be g times your mass times the radius distance between you squared. So you can see that the accelerations between you and the Earth are very different because your masses are very different, but the force is the same.
Okay.
All right. So yeah, no question? No. So I'm going to erase this. I'm going to try to write it much bigger so you can see it clearly on YouTube. Where's that test I did last time? Oh, it's right there. Okay. You guys ready for a tough question?
Mm-hmm.
Tough-ish. So you have, I'll do this over here. You have this sort of scenario. Very strong spring with a spring constant of 80,000 newtons per meter. It's a person who weighs 100 kilograms. Sitting right there. The height here is 10 meters. The angle here is 30 degrees, and there's a distance c that is traveled. So, that's okay. Right. So, the spring shown in the figure is compressed 50 centimeters. So we compressed it by 50 centimeters. Okay? And it's used to launch a 100 kilogram physics student. That's evil. The track is frictionless until it starts up the incline. So the only time there's friction is here. And the student's coefficient of kinetic friction on a 30-degree incline is 0.15. So mu k is equal to 0.15. Now they're asking us, calculate the distance s that the student travels up the 30-degree incline before he stops. Okay? And calculate the speed of the student at the bottom of the frictionless track. Point C in the figure. Oh, this is distance S, sorry. Okay. So, any ideas on how to do this? No? No?
Well, I think maybe because what are we looking for?
We're looking for the speed at the point C and how far up the slope with friction he goes after falling from here like this and being pushed by the spring.
What P plus U?
You can use like potential and kinetic energy. Like on top, from top there's height, so you can use h.
Okay. What else is there?
And kinetic.
Why kinetic?
Well, because you'll be moving.
But he starts from rest.
Oh, it's up from the rest?
He starts from rest, but okay. Technically he doesn't. Okay, let's just say he doesn't start from rest because there's a spring. Okay. He is at rest initially because the spring is compressed and he's just sitting there. But at some point the spring is going to release and like push him off.
So there's no kinetic energy?
Not initially, but after when the spring pushes him, there will be kinetic energy.
Okay, so he starts with potential energy and then he ends with no potential, just kinetic.
Okay.
So EI would be equal to mgh and then EF would be equal to 1/2.
Yeah, okay, so look at this. Here, I'm going to write it like this though. He has E initial is equal to, he has the energy stored in the spring, right? The spring has energy equal to 1/2 k delta x squared. That's how much the spring is compressed, and this is the spring constant of the spring. This is the potential energy US of the spring. Plus, he also has a certain amount of gravitational potential energy, GH. Now, when he gets to the bottom here, he's will have only kinetic energy, because the spring will be uncompressed.
But he said he starts from rest.
Yes, exactly. That's why I haven't put any kinetic energy in here. This is just the energy, the potential energy of the spring because it's compressed. The spring is initially compressed by 50 centimeters and he's sitting in front of it. Okay, there's a spring there. That's why I'm doing this. At the bottom, he's just going to have this kinetic energy, 1/2 mv squared. So as he falls to the bottom, because energy is conserved, you know that E initial will equal E final. So E initial equals E final. Then 1/2 K, I'll write it extra big so you can see. Plus mgh is equal to 1/2 mv squared. You want to solve for the velocity. That means velocity when he gets to the bottom at point C. We need that to know how far up the slope he goes. So, solving for V, we will get, essentially from here, I'll just write out that V is equal to 2 times all of this here, 2 divided by M, 1/2 K plus X squared plus mgh. This is all under the square root. Right?
You have 2 unknowns, right? Or one?
No, we know the height he starts from. We know the spring's compression. We know the spring constant. We know the mass. So we can solve for the velocity. I just solve for V. Okay. So let's calculate the velocity. The velocity will be the square root of 2 over his mass, which is 100, divided by 1/2. The spring constant is 80,000 times the compression is 0.5 squared plus 100 and 1.8 times 10. Anyone brave enough to enter that into their calculator? I'm pretty sure full screen you'll sort of be able to see that. It's been going for 13 minutes so far.
So they're looking for the velocity?
Yeah, the velocity at point C.
I have 19.8. I'm not sure if it's correct, but that's what I
Let's get a double check on that.
I have no idea.
Is that too much to enter into one calculator? You actually practice entering long equations. It will save you time if you can do them easily. You don't have to enter multiple times and plug into one and the other.
Yeah, I can see that.
It's good? Okay, thanks. 19.8 meters per second is the velocity of a physics student at point C. Alright? So now we know his initial velocity before he starts going up the incline. Okay? So let's yeah? Your hand.
Yeah, because I was looking at the board and
You're like,
thinking about
sliding up. Can we go? How far does he get? Okay. So look, clearly he has some kinetic energy here, okay? Kinetic energy. At the top he'll have no kinetic energy because he will come to a rest, right? Because of friction and because he's losing potential energy. Now notice that whether there was friction or not, just because of the fact that he's losing potential kinetic energy as he's gaining potential energy, he would eventually come to a rest at a certain height. Now the height he would have gotten to would be higher than the height he would get to if it was friction, because friction would be taking on extra energy, so he'd go less higher if there's friction. So now, the factors that are important for the amount of energy lost due to friction is the frictional force and the distance over which that happens, because that will determine the work. The work is force times distance. Yeah?
The velocity is where? At the bottom or at the right when he's...
Yeah, right before. Just consider that as his initial velocity before he goes up.
Okay,
Don't
so
worry about the angle.
it's not the velocity from right after the spring, it's after he's all the way down?
Yeah.
Okay.
I could have calculated the velocity that you'd have after leaving the spring. Then I'd have to take that velocity and add mgh to it, and then I would get this,
Okay.
the other velocity. So by doing this, I could just take the energy from this and convert it directly into kinetic. So I have to calculate, because I could have calculated, before he goes down, I could have calculated how much velocity he would have just from leaving the spring. Then I can calculate how much that velocity will increase by the time it gets to the bottom.
So it's V at C.
Yeah, so this V here is the V here.
Okay.
And that's his velocity as he's going. What the hell is that? Anyway. So that's his velocity as he goes up the incline. You got mail, baby. So here we are. Now notice that when he's gonna, so we have this one variable s. That's the distance along the slope that he travels, okay? But at the same time, he also goes up a certain distance here, which I'll call h, right? And if you look carefully at this, you'll see that h is really s times sine of 30, right? There's h, there's s, and there's sine of 30. So, if I move over here, let's look at the initial energy in the system. The initial energy is just his kinetic energy, which is 1/2 mv squared, which is 1/2 his mass is 100 times 19.8 squared. How much is that? Some value, some number, somebody will calculate.
I got a really big number.
Like what?
19,602.
Okay.
Does that make sense?
Yeah, that's pretty big. 19,602
602.
joules. Now, his final energy, the terms in it, is just mg times h, right? Because that's how high he goes from here to here. So, because he has no spring and no kinetic energy at the top, all he has is the potential energy mgh, which with the expressions we have is going to be mgs times sine of 30. So now we have an s in there. S is the distance from here to here. I'm going to call it d. So it's less confusing. This is a d. So this is actually a d now. Okay. Now we know that as he's on the ground, on the surface, I mean, we should draw a free body diagram just so you can see this. Here's the dude. I'll draw him as a box. Okay. So actually, I don't need to draw him as a box. This point. He's a dot. He's right here. His weight is like this. It's the angle of theta. Here, if I do this, this will be the normal force. Here we'll have a component Wx and a component Wy. Like that. Right? Everyone good with that? This is just an inclined plane thing. So you can see from here that the normal force exerted by the ground on him will just be the component Wy of his weight, which from this is the cosine of W. the angle of theta is the same as the angle of the incline. So now we know that his normal force should equal Wy. So the normal force is Wy, which is W cosine of theta. In that case, the force of kinetic friction is mu k times n, which is just mu k mg cosine of 30. Mu k mg cosine of 30. So now I have the force of friction between him and the ground based on his weight. Based on the normal force. So we know that the work done by friction will be equal to the force of kinetic friction times the distance d that he travels up the incline. And work is what kind of a force? Sorry, what did I just say? Friction creates what kind of work? Is it positive or negative?
Negative.
Negative because it takes energy away. It's non-conservative as well. So the fact that the work is negative doesn't necessarily mean it's non-conservative. It just means that it's taking energy away.
But when we're talking about like energy, shouldn't does that be just a number? Because you can't you say what's the energy in that?
Yeah, energy should be a number, yes, but when you're taking energy away, then you count it as a negative energy because you're losing that much energy.
Okay.
So it doesn't mean that we actually have negative energy, it just means that we're losing that much energy.
Okay.
We're losing that much positive energy. Now, what I was about to say about conservative forces is that in a conservative force, like gravity or the electric force or magnetic, if you take an object like this, in gravity, when I put it up here, it takes a certain amount of energy to bring it there. When I let go of it, it falls back down and it releases the energy that I stored in it. You see what I mean? The energy doesn't disappear. On the other hand, if I have this thing here, so basically, for me to bring it up here, when I let it go, it comes back down by itself. The energy gets released. If I bring this chalk over here against friction, it doesn't just come back by itself. I have to add more energy to bring it back. Energy was lost in moving it there. That's because that's a non-conservative force. Gravity is a conservative force because when I lift something up, it releases energy on its own. So the energy does not get lost. Whereas with friction it does. So if this is the work done by friction, I can rewrite this as mu k mg cosine of theta times d. And now I know that my initial energy and my final energy will be related by this. E final is equal to E initial minus the work done by friction. So this is very logical. Whatever initial energy I have, if I take away some energy by friction, that will give me whatever energy is left, E final. So let's write out all the terms. E final is mg d sine of theta, and that's equal to E initial, which is 19,602, minus the work done by friction, which we don't really know, we just have mu k mg cosine of theta times d. So you see we have two d's now, and d is what we're trying to find, right? We're looking for how high up the slope he goes. So because the height that he goes up to depends on the distance, that's why the d appears in two expressions here, and not only one. See that? Here the final energy depends on his potential energy, and there's a d because the d sets the height he goes to. But the d also sets how much work the friction force does. So that's why we have two d's, and we have to factor it and solve for it. So if I bring this over to this side, I will have essentially mgd, right? That appears in both. Sine of theta plus mu k cos of theta. that's equal to 19,602. I wonder if the camera can catch that last part. Yeah, it looks good actually. Okay. I'm going to erase this drawing. So, pretty much from there, I want to keep the D here and just bring everything else to the left side, to the right side, sorry. So we're going to have that D is equal to 19,602 divided by mg. So I'll just plug in the actual values now. 100 times 9.8 times sine of 30 plus UK is 0.15. 0.15 cosine of 30. It's a little messy at the end. Didn't get me. Plus 0.15 cosine of 30. There you go. So plug that in, and you've got your distance up the slope. Oh, I drink water. So
124.77.
1.77? Holy crap, okay, something's wrong. He doesn't. He can't.
Should I redo it?
Huh?
I'll redo it.
It's possible we just made the mistake somewhere else. It just seems like too far for him to go, you know?
Maybe I didn't put the brackets properly. But
It's okay because the actual problem solving
no,
part of it.
31.
31?
31.75.
Okay, that could work.
Yeah.
So D is equal to 31.75 meters. Alright, so that's sort of reasonable considering that the spring has a constant of 80,000 newtons per meter. And he does start pretty high up, so. And the friction, coefficient of kinetic friction isn't that high. But do you guys get the idea how what the solving was? No?
Can you re-explain the part of why the equation of energy, of total energy, why is that energy final equals energy minus work done by friction?
Okay, sure. So look, let's say I have something that's moving with a certain speed, that's the amount of kinetic energy, right? Now that object is flying through the air, and then suddenly hits an area where there's like friction or something. But the friction will take away some energy, right? So whatever energy I had initially, after it passes that region where energy is being used up, I'll have less energy. The amount of energy I'll have left will be the difference between the initial energy minus the work done by friction or whatever.
Yes, I understand what it's like.
Yeah.
We never think about putting all that together.
Yeah. So just always think of it like this. If I have a force that does positive work, it will increase the energy. So if I'm pushing a box in the same direction, I'll increase its energy. Then E final will be bigger than E initial. So because the work is positive, I just have E initial plus some work, gives me a bigger E final. If on the other hand I have a force that takes away energy, or is doing negative work, it will reduce my energy from E initial by some amount to a lower E final. So essentially, all this is saying is, whatever initial energy you have, if you add up all the forces and the work that they do, whether it's positive or negative, that'll give you the final energy that you have. So let's say that, yeah,
Okay.
let's say you have two forces. One does positive work, and the other one does negative work. The one that does positive work does 20 joules of energy, of work, and the one that's negative does only 10 joules of work. So the net amount of work done by the two forces is plus 20 minus 10, or 10 joules. So my initial energy will increase by 10 joules to my final being whatever initial was plus 10. So basically, if you have many, many forces doing different kinds of work, you just add it up, plus minus, whatever it is, and I'll give you your final energy. And so all I did here was I wanted to solve for the work, because I knew that my final energy was this, my potential energy, initial was given from before, and the word that my friction depended on the coefficient of friction, the normal force, and the distance traveled. Yeah?
Is mu k in the x direction? Is that why it has cos beside it?
No.
No. Okay.
So
And I don't know what we mean by normal force. Is that mg? Is
mg cos theta is the normal force. Because it's at an incline, if you have something that's on a flat surface, then the normal force is just equal usually to the weight, which is mg.
okay, so it's just like the same but opposite sign.
Yes,
Okay.
because the net force along the y-axis should be equal to 0. So n minus w should equal 0, or n is equal to w. But on an incline, what I was showing you is that when you have something like this, the weight is always down, but the normal force is not directly anti-parallel to the weight. So I can't say that normal force equals the weight in this case.
Oh, that's why you made a triangle.
Yes, that's why I made a triangle to show that this side here, which is the component of the weight that's parallel to the normal force, is Wy, and it's W cosine of theta. You see this, relative to this, which is the hypotenuse, this would be the x component of the weight. If my axis is y and x is like this. So then this, which is Wy, is W cosine of theta, and so my normal force is W cosine of theta. That's why I have coefficient of kinetic friction times the normal force, which is all of this, times the distance, which gives me the work. So that's it. I'm going to erase this now. You can relive the experience on YouTube later.
Can I ask something else very quickly?
Yeah, sure.
It does not make sense to like equate the.
Is it on the same problem that I only erase?
I have it, or you know.
You just sort of have to point to it, yeah.
Wouldn't it make sense to equate the initial kinetic energy, which is point C, to the final energy, just total final energy, which is potential at that highest point, and then find S without comparing it with the work done by friction?
You can't equate them because they're not equal to each other.
Why? That's conservation of energy.
Yes.
Right?
Yes, but the thing is, whenever you have friction, energy is not conserved.
Oh, okay, sure.
That's why you can't say E initial equals E final. You have to say, in that case, you say what I showed you here. E initial, E final equals E initial plus or minus the work when the energy is not conserved. Very good. Good call. So, now I shall do another question. Actually, I wonder if people could be watching this live from home or something. On a different website, you could on a different website. There's like live stream. Well, see you later. It's so funny when people just come in and like don't say anything and then leave. It's kind of weird. How are you guys with pulleys?
It's not like the analytical part I find hard. Like it's given to you in words. You need to like figure out what word means like to do what. How you're supposed to visualize it. I found that difficult.
I see.
Because when I tried drawing a picture and I draw it totally wrong. It doesn't work.
What? The chair? What did you say? You tried to draw what?
Like you know when you have a word problem
Yeah.
and then you kind of want to draw it out so you can visualize, so you know what to plug in where and whatever.
Yeah.
I find it hard to take the words from the question and to make pictures from those words.
Yeah.
I always draw it wrong.
It's a bit of a skill. It's a bit of a skill. I would say just reread it like 3-4 times and go very slow. Like it takes some practice to sometimes like get used to how everything translates from words to like the. But making the drawing is very important. At least you're doing that. Some people just try to start writing equations. They just write a bunch of formulas and try to plug things in and try to solve the problem.
Yeah.
It's impossible. It's too confusing. Okay, let's just try this one out, okay? Let's see what we can do. So this one you have. Okay. So you got 3 masses, M1, M2, M3, 2 pulleys, and a tension T1 and T2, and a coefficient of kinetic friction between only these 2 blocks of 0.3. So what do you do if you get this question on your test? Okay, what do you do usually when you have a problem? You gotta work on the problem-solving strategy.
Do they give you the maths?
Yeah, the masses are given.
Like
I didn't write them out, but they're given. It's the 2, 3, and 10. So the M3 is the heaviest.
What are you solving for? T?
They say, consider the figure below where the coefficient of kinetic friction between the mass M1 and M2 is 0.3. The hanging mass is given to be 10 kilograms, and the horizontal surface supporting the blocks along with the pulleys are frictionless. It says to draw the free body diagram of each block, identify the reaction pairs of force between the 2 gram and 3 kilogram blocks, M1 and M2. You look so scared.
Like you're supposed to figure out to draw it like that?
What?
Did they give you a picture?
No, they give you the picture there. Even then, you can still get it. You can still say, like, there's a block, another block, they're connected by a pulley, it'll be a little confusing. It says, apply Newton's second law to each block, and determine the magnitude of the acceleration of each block. So actually, the questions in here are organized in such a way so that the steps, it's based on the steps you have to follow to solve the problem. So, let's draw the free body diagram of mass 3. You have the weight W3 on it, right? And you have, going this way, T2. I've never put something that isn't a force on the free body diagram since it's just forces.
Okay.
Now, for the second 1 and 2, we have the weight M2, W2, and we have the ground pushing up with N, at N, so called N2. We also have the tension this way.
That's T1.
Yeah, T1. We have the tension in this way. T2. What else do we have?
The weight of mass 1.
Yeah.
And then you should have a normal force. No. Yes. The normal force should be greater because it's not just the weight of mass 2. It's the weight of mass 2 plus the weight of mass 1. So the normal force should be greater.
Yeah. Well, the normal force will be greater because when you equate N to this, N will be this plus that. So it's already graded by just from here. This plus this will be equal to this. So the normal force is greater. So now, this is it for this one. The other block will have its mass.
Is that WC or W2?
Where? This?
Yeah.
W2.
And W1?
Yeah. So in this one we're going to have the normal force M1. This is M1. And we have the tension this way, again T1. And this way we have the force of kinetic friction. Anything else?
I don't get how you know that. Like, where did the W1 come from on the M2?
Oh, because this box is on top of this one, so the weight of this one is pushing down this box.
So then how come you have to draw M1 separately?
I'm not actually done with M1, but I'm just...
Okay. Like, you don't, would you consider M2 and M1 to be just like one thing?
No, separate. Yeah, because they're free to move on their own. They're not connected.
Okay.
So the reason I put... Actually, did I do that wrong? Because this is going to be moving... See, look, what's going to happen is this is going to move down. This is going to move this way. And if this moves that way, this rubber is going to pull this that way, so it's going to be moving like that. So there's going to be a force of kinetic friction on this one that way. Whereas on this one, because it's moving that way, this one will have a force of kinetic friction in this direction.
You usually draw it. Is the force of kinetic friction going to be the same for both?
Yes,
Yeah.
it'll be the same. Because they're both between this and this, the normal force between them is the same. So the normal force of, well, what will really count is the normal force that this one is experiencing. N1. And that is as a result of its weight, W1. So, as you can see here,
How come that one has FK and not T2?
So I should run it here, FK2, FK1. This is FK2. How come what?
Where does the FK?
There's friction over there?
Yeah,
How come?
there's friction between these two here. So just like that.
Okay, but
So look, the first one has its weight and the tension going up. Oh, then the second one is here. It has the tension going this way and the tension going this way. This is T2, this is T1. So that's why I put T1 and T2. Then this one has the tension pulling it to the left.
I'm talking about the friction though.
That's why I put it here.
Oh, okay.
I'm talking about the friction too. Where's friction too?
Well, technically, I can read them as friction. I can call them both friction 1 because they're really the same thing. FK1. That's just the friction between this one, which is being pulled, the friction to the right, and the friction is to the left between here.
The friction on top of the box, the second box, like the box is sliding, the box is going this way, right?
This box is moving this way, and this box is moving that way.
But the friction on the top of the box is not affecting the box moving this way.
Yeah, it is.
On top of the box.
Yeah, it's holding it back. Let's say you're trying to slide this desk this way, and I'm holding my hand and pushing like this. There's going to be some friction between my hand, and then it's going to hold it back.
Okay.
Right?
Okay.
Either way, it's not the best example, but it's enough that it will make a difference. If my hand wasn't there at all, even if this was in the air, you could just move it around. If I just put my hand in it, you have to overcome the force of friction between my hand and the block and the table. Whether or not I'm actually pushing it against the ground, even if it's just in the air, it'll still be an extra force that you have to surpass.
What are you solving for?
They asked us to do the free body diagrams to show the reaction pairs, and to write up Newton's second law, so I think it was MA, and then to find the magnitude. So really what they're looking for is the acceleration of the whole system.
So they want you to draw these on the exam, right? They want you to, like, these things here, that would
Yeah,
count
this
for
is what you would
marks?
draw. Yes. Free body diagrams will definitely count.
An acceleration of what, exactly?
Of the system, of the pulleys, of the blocks, yeah. I'm going to stop this and then let it upload now, so that in case if it goes bad, it hasn't gone bad yet, and then I'll just make a second one. So it'll be like part 1, part 2.
These are really hard.
This one? Yeah, it's a bit hard. I chose to do it because it's on the exam, and then if you can do this, the easier ones should be easier. Okay.